Okay, this is the Unit 3 Mastery Project. This is FAQ number 4. And they're telling us that block 1 of mass M is at position x is equal to 0 on a horizontal surface and is contact with an uncompressed spring with spring constant K. Block 1 is pushed to the left along the spring from position x equals 0 to x equals negative d. As shown in the figure 1, compressing the string by an amount delta x equals to d, there is negligible friction between the surface and the block 1 from x equals to negative d and 0. There is non-negligible friction between the surface and block 1 everywhere to the right of x equals to 0. The coefficient of kinetic friction between the block and the surface everywhere to the right of x equals 0 is mu k. Block 1 is released from the rest position x equals to negative d. When it is at x equals to 0, block 1 loses contact with the spring and enters the rough part of the track, eventually coming to rest at position x equals to 3d. Now part A says block 1 is replaced by block 2, which is made of the same material as block 1 but has a mass m such that capital M is greater than lowercase m. Block 2 is pushed against the spring until the spring is compressed by an amount delta x equals to d. Block 2 is then released, slides across the track, and eventually comes to rest. Indicate whether the position x2 of block 2 when it comes to rest is greater than, less than, or equal to 3d. Here it should be less than 3d because since the amount of energy stays the same, and the mass of block 2 is greater than block 1, it's a greater force of friction will be applied to block 2, therefore dissipating quicker and resulting in a shorter distance traveled. And part B says, starting with conservation of energy or the work energy principle, derive an expression for the final position x2 of block 2. Express your answer in terms of mkd, mu k, and physical constants as appropriate. So here we can first start off with the work in is equal to the work out. And the work in is the potential energy of the spring, so US is equal to, and the final velocity, the final kinetic energy, so K, F, as well as the work done by friction, so plus work F. And then know that the potential energy of the spring is equal to 1/2 K delta X. The delta X, they tell us, is just D, which is the length of the compression. So we just put D squared is equal to, and since the block stops moving, there is no final kinetic energy. And the work done by friction is just the force of friction times the distance, which is a distance x, or wait, x2. And then if we do the quick free body diagram, a quick body diagram, we have here Fn, normal force. This is Fg, gravity, and this is friction, Ff. And then we know that friction is mu sub k Fn. So if we just on the y component of this, we'll get mu k f n minus mg is equal to wait a minute. I, this is not here. So it's just an Fn is equal to mg, and we know that friction is mu Fn. So then right here for work of friction, we could just put mu sub k mg, which you got from right here. So we just replace Fn. Here, just make it make more sense. We replace that right here, and then as well x2. And then now we're solving for x2. So if we isolate this, we should get x2 is equal to kd squared over 2 mu k mg. This should be capital M. Capital M, d mu k, g's are constant. Yep, this should be x2. And the final part is to justify how the expression to derive for x2 justify how the expression to derive for x2 you derive. So how is this equation consistent with what I said in part B? Oh no, how is part B consistent with what I said in part A? So part A, I said that since the mass is greater for block 2 than is block 1, then the final distance should be lower for block 2. And this is true because, as you can see here, the distance x is inversely proportional to the mass m, meaning that the greater value the mass is for m, the lower value x2 should be. So it is consistent. And then that is everything. Thank you.